Okay, hello, welcome back. I'm back. So this is the first video in a series where I will be discussing autonomous control and how to code up sort of a quasi video game. It's not really a video game, it's more just a simulation of a physics model. And firstly, control it through autonomous methods, control it using PID control, control it using state feedback with a linear quadratic regulator, and how to use Kalman estimators to improve that type of control. And then finally, we'll be looking at how to use input from a joystick like this one to actually fly our little creation. So go ahead and join me here as we get started. All right, so here we are. Let me go ahead and open up MATLAB here. And this is Simulink. So this is a model that I made that I've already written that basically does everything that I want to do. This uses PID control with transfer functions and then a simulated model that the controller actually can stabilize. So if we go ahead and look at what this thing looks like, we can see here that I have got a basic, really super basic 3D world. It's nothing fancy, but what I can do is I can control this vehicle using my joystick. So I can actually, I'm communicating with it. You'll see later how we set this up, but in such a way that its onboard computer is fully stabilized in the flight. And if I want the onboard computer to take over, all I have to do is let go of the controls. But if I do take the controls, I can go ahead and fly it this way. I can fly it this way. And the altitude change is also me. I have a throttle here that I can use to regulate the altitude. And the way that I'm controlling this is I'm actually reading the inputs that I want into the set point of my system controller. And I'm not very good at flying this thing yet. It's I could definitely improve sort of the actual dynamics of it. But you can see that I can fly basically whichever way I want, and I can change the altitude. The way I'm doing this is I'm feeding in the inputs from this joystick into a set of integrators, and those integrators add up the inputs that I give into the controls set point. So if I just let go, the value that is currently programmed in as of the value that the system is being told to go to when I let go of the controls is actually the value that the software latches onto and stabilizes. So there are a few different versions of what's going on here. So what I can actually do is if I remove the joystick, if I just don't use the joystick input, if I instead command the system through a list of set points, I can, right now I'm just doing this through manual entry. Obviously in the future, you could set up this was designed to read out of a mat file, so you could load in a set of coordinates and it would fly to it. Actually, I'm going to be communicating with this through, my goal is to communicate with this through a guidance algorithm that I've written over here, that actually calculates what those set points should be for another project that I'm working on. But right now, let's just go ahead and make this thing fly, lift off, and then say fly, and then land. And the reason I set up those points was because I have... Okay. Oh, I don't need that space there. Well, I don't know. This doesn't seem to be liking my use of... Oh, duh. There we go. Alright. And if I go ahead and load this, I run this. Well, that's actually a function. I don't need to run it. Alright. Now I can go back to that simulation and watch what happens. This time I'm not using any in-control inputs. And immediately we can see the vehicle takes off and flies over this, the green pad, and proceeds to land on it. Now it's not perfect because the mixing between actually what's happening here is my CAD model isn't centered perfectly. But, yeah, it'll go ahead and minimize this error actually. So if we want, we can just go ahead and actually manually just finish it off. What's actually happening was I reduced the gravity for this simulation, and so I didn't retune everything with those new gravity settings. But you get the idea, right? So now we can say fly through that hole and bye. All right, so how do we get there? So this is the same, well, a very similar system, but in state space. So rather than using a bunch of, so in this algorithm, I use a bunch of functions that I wrote to convert my thrust inputs into angular speeds, accelerations, and linear accelerations, sorry. And then I use just some integrators and some coordinate frame stitching to transfer those into some coordinates that I can output as an animation. I understand I'm going over this at a very high level. I haven't explained what any of this does, but just bear with me for now. I want to break up the software that we're working on into 3 different segments, and this is going to be true for all the software that we make. Well, until we start doing sort of navigation things where we do have more sophisticated methods of calculating where we are. Okay, so the first thing that the algorithm needs is it needs what I call the guidance algorithm, and that is it can be a simple function, it can be a simple data entry bar, or it can be something more involved like what I have here. But basically what it needs to do is it needs to be able to tell the system where it needs to be. So what this outputs is an X, Y, and a Z location of where this block wants the system to be. It has some errors, troubleshooting outputs as well that I'm not currently using. Okay, and what does it input? Well, it can see where the vehicle currently is in space. I won't get into how you would actually determine that in the real world. In our algorithm, we just use a physics model to calculate it. And then I can see the velocity as we cross each of those points. So, yeah. All right. And then what I do here is I discretize the incoming signals so that they're in step format rather than continuous, and that just makes our integration slightly more robust so that we don't have to worry about minimum error deviations where we get these very tiny numbers and we're dividing by very close to 0 and stuff. And then all I do is I literally just take the derivative of each of those inputs to feed my derivatives, which are the same as velocity. All right, then so you can see here, this is actually the input from my joystick. So let's go ahead and disconnect that. I'm going to go ahead and disconnect the joystick input from all of my system. And then what we can do is go ahead and update this so that I'm going to include the error. So previously I wasn't looking at the error term in the Z direction. I was only looking at X and Y. I'd written the code for Z, but to do better manual control, I wanted the Alex software to be able to work even if I was changing the throttle settings. Okay, so I'm going to go ahead and add in the absolute value. Oh gosh, I can't type. I have this joystick in front of me. And let's go ahead and put in the error in the Z. Okay, so you can see I calculated the error in the Z, but basically what I did was I said error in Z is equal to Z minus PZ, where I am looking where X, Y, and Z are the set points that I'm reading from a matrix. So this is basically XYZ1, XYZ2, etc., etc. Now the goal is that this matrix here, you could read this from whatever you wanted. So if I have another function, I could say A is equal to, and then I could just say some function. And then that function will tell me what my proper trajectory should be. Like for instance, this function over here does exactly that. Okay. So, and then down here I can tune how sort of picky I am about my errors. So if I sort of up these gains, what I can do is determine how picky the system is about how close I've got to be to the set point before it can progress to the next set point. Again, we're going over this at a very high level. You don't need to understand sort of how all of this code works. Right now, we just want to look at what it does. So now that I have that function, and by the way, this is the basics of GNC, or Guidance, Navigation, and Control. It's a field of programming and sort of engineering that deals with controlling and stabilizing vehicles, typically in either like an aerospace application. One of the critical things about guidance, navigation, and control being different than just control is that, say, something like a quadcopter has a much easier way of determining, which way is up and where it is in space than a satellite does, for various reasons. So GNC allows you to firstly navigation, where should I be? Guidance, navigation, where am I? Guidance is where should I be? And control is how do I get there? So where should I be right now? Our entire navigation algorithm our entire guidance algorithm just consists of this block, essentially, where it says where I should be is whatever comes out on these rails. Okay. Once the signal comes out on those rails, I feed it in through a set of time delays. This is so I don't error shock the system. So when I update to the new set point, there's a time delay associated with it. So if I go ahead and say step plot this function, let's go ahead and just step plot it. Look it up there. All right, let's watch what happens. So if I just basically, what the step plot is, all I do is I input a step into the system and I watch how the system responds. So we can see that the input was, I'm going to go ahead and change this input to 2 so that you can see exactly how that is working out. And you'll get very familiar with this concept of step plotting if you follow my video series. So while I'm setting this up, let me just rehash sort of what the goal is for this series. My goal is to teach you, whoever you are, if you have a fundamental understanding of dynamical systems and maybe some differential equations, how you can take that mathematical knowledge and convert it into some very valuable engineering skills, programming skills, and some basic animation skills. I want to look at projects that you can do in a virtual world. If you, say, for me, don't have access to the physical tools that a lot of people do for sort of doing these things on like real rockets using vectored thrust or quadcopters. If you're, completely broke and all you have is your computer, well, you can still have a lot of fun. And you can actually have a lot more fun because you can do a lot more sophisticated models than you'd be able to run on real hardware, like, say, an Arduino, which I've got several of around here. Dang it, why can I never find things like that? Oh, right. Well, my desk is a disaster. Okay. You know what? It looks like it doesn't want to be found right now. I admit to owning, I think, 9 Arduino Nanos. I always get them in like the multi-packs. Okay, so if you don't have hardware like that, what software like this will allow you to do is to write all the same code. So the blue line is the step. So if you see this, the blue line is what the commanded value is, and the yellow line is what the system actually sees. So you can see that instead of error shocking the system with this massive change, over the course of 50 seconds, I am gradually inputting that set point value. And you can see the same thing happens for when I change my step. So you can see that it moves pretty quickly, and it's okay to move the set point fast. It's just if you understand, how calculus and sort of functional analysis works, it's very difficult to process sort of algebraically these, discretized inputs. It's much more easy to work with continuous inputs. So even though this does have a bit of a jump here, through time, see, if we have instantaneous points, it's okay to have a jump. Okay, like a break like that. We can change by 90 degrees, but it's not a good idea to change by 90 degrees twice in a row. So we don't want to go jump and then jump. We can have one jump, but we want it to be smooth for our system. And we'll go ahead and look at that later in a different video. But again, this is sort of just an overview video. I'm just sort of want to go through how this software works. And let's go ahead and stop the model so it's not slowing my computer down. I do have a really nice desktop for this. But you can do this on most computers, just you might have to tweak with some of your settings to make it work really well. Okay, so once we determine where we're supposed to be, I use this this input processing box, which essentially, if you looked at my vehicle, so basically what I have is it's kind of like a lunar lander with 8 rocket engines. So instead of using vector thrust, it uses differential thrust. And so what this does is it processes my input commands uses some algebra and some basic delays. What these do is they simulate the performance of a real-world engine. So obviously a real-world engine can't respond right away. It can't, you can't have a negative rocket thrust, and there's going to be some delay associated with your inputs. So this allows me to model essentially all of that. Okay. So then when I've processed that data, I feed those into another block which computes from each of the individual actuator inputs. This is engine 1 through 8. So this is the thrust level in each of the engine. It converts those into a thrust and torque about the vehicle in the vehicle's home coordinate system. So one of the concepts you'll get very familiar with if you study guidance, navigation, and control is this idea of coordinate frame stitching. So if I have one coordinate frame that's represented by my vehicle's cardinal axes, so like for instance, say this vehicle is just fixed in space, right? The z-axis is always going to be right up on the vehicle, right? It'll have some x and some y-axis, and no matter where I move in space, that coordinate frame is slave to that vehicle, right? It's not moving around. However, the vehicle is moving around. So if I want to be able to incorporate my measurements in the real world into my algorithm, unless I want to do, sort of really involved trigonometry in between, which can give you singularities and asymptotes if you're not using quaternions, what you can do instead is to calculate all of your parameters on the base vehicle and then stitch, that's the word that I use, stitch those values into another coordinate frame using a rotation matrix, using a homogeneous transform. There's different techniques you can use, but essentially it allows you to convert your measurements in the system to achieve much better and more accurate control positioning instead of control estimation. So if you want to estimate where you are in real space, that gets hard. But if you can just measure where you are in real space and then stitch the two coordinates together to give you, your final output, you'll have a more accurate system. Okay, so then what this block does is it uses some physics to convert using the dynamics of my model, so some moments of inertia, and then some predefined mass terms. It computes my angular accelerations in x, y, and z relative to the vehicle, and then it also computes. And by the way, these values are not slave to the axes, by the way. So when you calculate an angular sort of rotation, your angular acceleration, that acceleration will be true in any coordinate frame. As long as you're orthogonal. As long as you have orthogonal coordinate frames, you can, in other words, your absolute Euler angles are going to be the same, pitch, roll, and yaw. If you're integrating them, that is. Okay, so then what I do is I integrate those out to get my angular errors, or my angular positions. So I convert firstly from MATLAB to another coordinate system, and then I rotate them from Euler angles to a rotation matrix, and then I use that to firstly calculate, the rotation for my animation, and I also use it with another. So before I do that transformation, I firstly multiply this rotation matrix by my positional accelerations to convert my linear accelerations from accelerations in the coordinate frame of the vehicle to the global coordinate frame. So instead of measuring them from the coordinate frame of my rocket ship, it's now this coordinate frame where actually, because it's in this animation program, y is actually the up direction. So that's why I have to have this little block here. Because it converts my MATLAB coordinates, which have z is up, into this other system, which y is up. But anyway, then I use a bunch of sort of signal expanders and decomposition to process all of my signals to also scale the size of the flames coming out of this. So I don't know if you can see, but there's actually flames that come out of the bottom, little orange things, and they actually change size based on the thrust inputs. It's not perfectly tuned in this model because I didn't design it for this model. I just grabbed this model and put it in this animation for today's video. Okay, so all right, so then what I do with the positional accelerations, well, once they're stitched with the real-world coordinate frame, then I go ahead and double integrate them to give me position values based on some initial conditions. So this way I can add initial conditions to the system. And I have these, by the way, for both the angular values and the positional values. And then I scope them, so I make a scope that allows me to look at them sort of in this space. And then finally I feed them into the translation of my animation. Well, then what do? Well, now that I have all these values, I'm using a closed loop controller. So I go ahead and tap all of these output values and put them back into my controller. Now, firstly, I have my angular controller, which is this series of controllers. What this does is it controls my rotation about the X and Y axis. It stabilizes my vehicle about the rotational axes. So if I input a set value, it's not just gonna keep spinning, right? It's gonna, it controls my, it intakes an angular set point, so a value in radians, and then it basically changes the input to the vehicle, inputs to the vehicle until it matches that that input value. All right. And then of course it takes and then of course I tap some of these values back into my original guidance algorithm, which then can look at, are we where we want to be yet, or do I need to keep iterating the system? And this is pretty fast. It's a pretty fast system. It works pretty quickly. This is my set of angular regulators, and then I regulate where my angular set point should be by using this other algorithm. I believe this is called servo control. I don't know that for a fact, but I believe this technique of using one set of controllers to regulate your sort of positional, because if you have a vehicle that has thrust, if you angle it, that thrust is going to be off an axis. So you have one set of controllers that controls your thrusts in the different axes, and then you have another set of controllers that determines what that thrust should be.